Hey all. Since we didn't get to go over really any of 4.2 in class, I wanted to give a very quick or sort of efficient run through of the problems to try to give some insight into what the solutions are. Now, numbers 1 and 2 are really straightforward. They're just straight up conservation of momentum problems. You have in number 1, you've got two objects, an orange billiard ball and a blue billiard ball, and after the collision there are still two objects. So you've got just a straight up some kind of a bouncing collision where you've got object 1 and object 2 collide. They each have their velocities before the collision, and then object 1 and object 2 each have their own velocities after the collision. You got everything except for one of the velocities. Number 2, you've got two objects before the collision, the puppy and the frisbee, and they're heading towards each other, and then afterwards they are combined because the puppy catches the frisbee, and so they are going to be moving at some common velocity. The two objects together have a combined mass moving at some common velocity. Number 3 is where it starts to get interesting and a little more challenging. This 30-gram dart is shot straight up. At the same instant, a 20-gram cork ball is dropped from 3 meters above the dart. What are the speed and direction of the cork after it's hit by the dart? So you've got something being dropped and something being fired upward, and they're going to meet somewhere in the middle. Well, the first thing is we need to know at what time and or what position they actually are going to meet each other. So the first piece of this problem is really kinematics, where the bottom object starts at 0, a height of 0, and the top object starts at a height of 3 meters. And this position in the middle, let's call it X, is where they're going to meet. And so if we create a function position as a function of time for each of these, the cork ball is, so we've got its original position, 3 meters. It's got no initial velocity, plus 1/2 at squared, so 1/2 of gravity is -5, so 3 minus 5t squared. So we've got an expression for its position. And an expression for the position of the dart is starting from a position of 0, so its original position is 0. It initially has a velocity of 9, so VO times t is 9 times t, again, minus 5t squared, because 1/2 at squared is still the same thing, behaves the same for both. And so we've got an expression for the position of the dart. And the point where they meet is where those two positions are equal, where the cork's location is equal to the dart's location. So we solve for time, and it turns out that that's going to be at a time of 1/3 of a second. Now we can actually get into the momentum part of it. Well, almost. Now we got to find out how fast each one is going at the moment of the collision. So again, using kinematics, we can find that the velocity of the cork is -3.3 meters per second, and the velocity of the dart is 5.67 meters per second. Now, finally, we can get to the actual momentum, because we need initial velocities to answer our question. We know that they're going to be combined afterward because the cork, the dart sticks into the cork. And so this is really all about what leads up to the momentum part of the problem. Got to do a whole bunch of kinematics to figure out where and when they hit, what their velocities are at that moment. Then you can solve the momentum piece. Number 4, we've got two-dimensional momentum. We've got two objects which combine. Let's see. Collides with and holds on to, right? So two people are coming towards each other at a right angle, and they stick together and move off in each other's arms. as they careen across the rest of the rink. And so one thing that we got to figure out is what is the final momentum, and more specifically, the direction that they're traveling. So this is pretty straightforward vector addition. We've got an upward vector and a leftward vector, and combined they will give us the resultant vector. And there's a couple ways to go about it, but I'm going to just say the short version, and that it's just vector addition. So figure out what the final momentum is using vector addition, and most importantly, what the angle is, what direction are they traveling, and that will tell you where they're going to hit on the edge of this circular rink. Two ice skaters with masses of 50 and 75 kilograms are at the center of a rink. They push off each other. They glide to opposite sides. Well, because initially they're at rest, the total momentum is 0 because their velocities are 0. So that tells us that the momentum of one person going in one direction has to equal the momentum of the other person in the other direction. So we have most of what we need. We've got the masses, and we've got oh, we didn't actually have the time yet, or the velocity yet. So I guess we need to determine the velocity. So how do we figure out the velocity? Well, the mass times velocity of one person should be equal to the mass times the velocity of the other person. But if we substitute in the formula for velocity, distance over time, we can figure out how far they have to go and or how much time it takes to get there. Let's see, they started at the center, and they both reached the edges of the rink. So that tells us that the distance that each of them has to travel is the same. So by plugging in distance to this formula, or by recognizing that the distance is the same, that tells us that the distances cancel out. So what we're left with is negative m1 over t1 equals m2 over t2. And if we rearrange things, we get m1 times t2 equals m2 times t1. Rearrange and solve for the thing we know. So we have T2. We know the amount of time that the 75 kilogram person took to reach the edge. That tells us that the other person is going to get there in less time. As you might expect, the person with less mass is going to go faster. They will reach the edge of the rink in less time. And so where does that get us? Oh, now that we know the time for the 75, we know, what do we know? We know the, where does that get us? Oh, I guess that's it. Oh, that's my or. Yeah, I guess there's multiple ways to figure this out. All right, but that's the version I'm going to go with. Number 6 is, again, two-dimensional, where initially in both x and y directions we have 0 momentum because it is not moving at all, and it blows this into 3 pieces. So in the x direction, we only have 2 pieces moving in the x direction. So P2 and P3x have to be equal in magnitude to each other to offset each other. And we have some information about those, so plug in, chug. And in the y direction, we know that P1 and P3y have to be equal to each other. So in this way, we're finding out something about P3x and P3y, and then finally in the end, we can put those pieces together to know something about the velocity of that object, the velocity of object 3. Number 7 is, again, two-dimensional. I'm not gonna go into all the details. I think it's somewhat repetitive from the previous two-dimensional ones. They're not that conceptually elaborate. You just gotta do all of the momentum in the x direction, and then separately from that, do all of the momentum in the y direction. And then finally, once you have some x and y component in the end, you can put those together to get your final answer, which will be in 2 dimensions. Number 8, I always kind of think these ones are cool because we don't usually think of momentum in momentum problems, things crashing. We don't usually think of them as going through each other, but they certainly can if we're talking about a bullet and a block of wood. And so the bullet in this case is going to go through the object. And of course, by going through an object, the bullet's going to be going slower when it emerges from the other side. And of course, the movement or the motion of the object itself is going to be altered through that interaction. And so we're given the velocity as it goes in. We're given the velocity as it comes out. We are given somehow we got to find the time that it takes to get through there. And we're given the distance that it travels as it goes through there. Granted, there's a little bit of hand waving here because as the bullet is moving through the block would be moving, so technically it would be having, if we sort of pushing the block along, it might actually travel more than 30 centimeters as it moves through the block, but hand waving aside, it travels 30 centimeters through the block. And so using whatever kinematics you want to use, we know the initial velocity, we know the final velocity, and we know a distance that it travels to undergo an acceleration, and we can find a time through kinematics. And using that time, well, the impulse, the force times time, is going to be equivalent to the change in momentum. So we've got its mass, we've got its change in velocity. Now we have its, and we also now have its time. One question that somebody asked was, could you do this with just kinematics and forces? And the answer is absolutely yes. F equals ma, we would just need to know the acceleration. So F, the force, would be equal to the mass times Vf minus Vo over t. And of course, we have all of those things. Well, if you take a look at it, you might realize that, in fact, these are the same equation, because all you do, if you multiply the t over there, you got F times t equals mass times the change in velocity. So, in fact, F equals ma and this impulse equation are literally the same equation, just with some rearrangement. So that's a fun insight. And lastly, part C is just straight up conservation of momentum. Number 9, I did a whole video on by itself. Number 10. How much further do we have to go? 10 and 11. A weather rocket accelerates upwards. Ooh, that's quite fast. It explodes and breaks into 2 fragments, one twice as massive as the other. The lighter fragment travels straight up. The other fragment, where does it go? So, given the acceleration and the time, we will know at what height this explosion occurs. We're already given the time. And so I guess then the important thing is, what are the velocities? I guess we don't need to know what the height is. We need to know what is the velocity of the things, what are the velocities of the things at that moment. And so on its way up, that's basically a kinematics problem. What do they do here? I got VF, 0, VO. Oh, I guess I worked backwards. Oh, yeah. Ah, yes. Work backwards. So, using the lighter fragment's velocity at its peak, at its maximum height, is 0, because it's at its peak. We would like to know its velocity at the moment after it exploded, plus 2AD. All right, so 2 times the acceleration is negative 10. D, 510. Where's 510 come from? Uh, oh, yeah, I did do some kinematics to find the height and the time that it exploded at. Right, so given its acceleration and 2 seconds, we can find that it was moving at 20 meters per second at the moment of the explosion. And given that same information, we can find that it was 20 meters off the ground at the moment of the explosion. So if the small fragment reached a maximum height of 530 meters, that tells us that it went 510 meters above the explosion point. So, working backwards from its maximum height, 510 meters above the explosion point, we can find the small fragment's velocity immediately after the explosion. So, the small fragment's velocity after the explosion is 101 meters per second using kinematics. Now we have the total mass. We know the velocity just before the explosion, found using kinematics. That was just before the explosion. So we know the velocity before the explosion. We know the mass of each individual object, and we know the mass of the small piece. So a handful of kinematics is needed to fill in all the details. So we're starting from the beginning chronologically. A large object is launched upward. It breaks at some point in space and time, at a time of 2 seconds and at a location of 20 meters, and it happened to be going 20 meters per second there. We found all of these by kinematics. And then it explodes, and the small piece goes way up, and the big piece does what? Well, that's the mystery. We would needed to know what's going on with the big piece. So using more kinematics, we find that the small piece is working backwards from its peak up here. We find that the small piece's original velocity at the moment of explosion was 101 meters per second, and that is the velocity after the explosion, which then allows us to figure out what was going on with the big piece immediately after the explosion. And lastly, number 11, an object at rest on a flat horizontal surface explodes into 2 fragments, one 7 times as massive as the other. So all we know there is that the mass of the big is 7 times the mass of the small piece. The heavier fragment slides 8.2 meters before stopping. Before stopping. That implies that there's some friction, some work being done. And we want to know how far the lighter fragment is going to go. They have the same coefficient of friction. Okay, so as there often are, it's more than one way to go about this. You could use energy or you could use kinematics. Certainly, whatever you do, you need to know momentum to recognize that if we start with 0 momentum beforehand, the momentum afterward needs to be 0 as well. If one of them is 7 times as massive, the other one's going to be going 7 times as fast. Okay, so that tells us something about the initial velocities of each one. Using energy, for example, well, given the velocity of each one, that tells us something about the kinetic energy. And all of the kinetic energy of each of them is going to be dissipated by friction doing work. So we've got mu times N, that's the force of friction, times D. So friction times D, force times D, that's the work being done by friction. So the kinetic energy of the small piece, 1/2 mv squared equals mu times mg times d. The m's cancel out because it's the same small piece. And we can solve for the distance that the small piece goes, and using the same analysis, we can solve for the distance that the large piece goes. Although I guess we knew that. Oh yeah, the heavier piece we already did know, right? I'm running out of steam, but maybe this helped. Hope so. Talk to me if you have more questions. Have a great day.